Welcome to this pre-lab video on the conductance of salts. The diagram here shows a conductivity cell. When a voltage is applied between two electrodes in a solution, it induces negative ions to migrate towards the positive electrode and positive ions to migrate towards the negative electrode. This movement produces a current, and the resistance gives a measure of how difficult the motion of these ions is. We can measure the conductivity of the solution, symbol kappa, by the equation shown. Kappa has units inverse ohms per centimeter if we are using centimeters for the distance traveled. The reciprocal ohm to the minus 1, is given the name Siemens, symbol S, giving kappa units Siemens per centimeter. The molar conductivity will depend on the concentration, as the higher concentration means more ions in solution. Therefore, we can define the molar conductivity lambda m to account for the concentration. As we'll see in a while, the units here are moles per centimeters cubed, so that we have consistency in our units centimeters. Experimentally, conductivity is easy to measure. Examining the probe carefully, we can see the two electrode plates. It is important that these are fully immersed in solution being measured, and that the measurements are conducted at a uniform temperature. You'll note here that we're using an AC power supply. This is used to prevent any reaction due to electrolysis. An important step is calibration. We use a calibration with a common standard potassium chloride, which for a 0.01 molar solution has the conductivity shown. When we're setting up the instrument, we set the instrument so that we reach this value, and then we can usually repeat it at the end of the experiment as well to ensure that there's no deviation in this value as the experiment goes on. We also went through the experiment at constant temperature. So the apparatus allows you to prepare each of your solutions in various plastic tubes and then immerse these plastic tubes in the water bath. You should make sure that you note the temperature for the readings when you take them, because the conductivity will of course depend on temperature. One of the major sources of experimental error in this experiment is cross-contamination. You need to make sure that you wash the electrode very well with the deionized water provided. Okay, so when you get your data, when you measure the conductivity kappa in microsieverts per centimeter for all of your salt solutions, you then want to calculate the molar conductivity and the limiting molar conductivity. The molar conductivity will be calculated by dividing kappa, the value you measure with the instrument, by the concentration. And remember, the concentration will need to be in moles per centimeters cubed. We can then calculate the limiting molar conductivity using the equation shown. The parameters involved are given in the manual. But it's important to note that this equation shown, the Onsager equation, is a linear equation. And we can see here on this graph that actually limiting molar conductivity is the highest molar conductivity that we will find for a sample. And the reason is that limiting molar conductivity assumes that the ions are far enough away from each other that they do not interact. So the positive ions moving one way do not interact with the negative ions moving in another way. Therefore, there is no limitation to their flow. So we find that the limiting molar conductivity is a higher value, it's the highest value on this plot. We're going to calculate it using the equation, but of course we could calculate it experimentally by varying our concentration of our salt across a range of concentrations and plotting the molar conductivity as a function of the square root of concentration. The y-axis intercept of that plot would give us the limiting molar conductivity. While we don't have to do that, because we're just going to calculate from the equation, what you are asked to do in your discussion is to explore Kohlrausch's law under limiting conditions. This is basically asking you to see, is there any difference between the individual ionic mobilities contributing to the overall molar conductivity, and the manual describes how you might do that.